In the last video, we looked at how to calculate reactions from point loads. In this video, we're going to look at how to calculate reactions due to distributed loads, or loads that are not directed at a single point, but rather distributed over some length on our member. Again, we will only look at simply supported beams and beams that have only two supports. We will also only look at examples of linear uniformly distributed loads. Let's start with a solid beam that is 10 meters long and has a UDL of 5 kilonewtons per meter. The beam is simply supported by two supports at each end of the beam, labeled as support A and support B. So how do we calculate the reactions from these supports due to the weight of the beam? We'll start by drawing a free body diagram of the beam as an idealized beam and showing all of the forces acting on it. The weight of the beam is distributed along the entire length of the beam with a uniform distribution of 5 kilonewtons per meter. We can represent this as vertical red arrows pointing down of the same length and evenly spaced along the beam as shown in the free body diagram. Due to the UDL pushing downwards, the support will produce opposite reactions, shown here as RA and RB pointed upwards. So to solve for the reactions RA and RB, the trick is to first convert the distributed load into a point load by determining the magnitude of the total load and the location that this load acts on our beam. So to determine the total force due to the UDL, we simply multiply the UDL by the distance that the UDL acts. In this case, the UDL is 5 kilonewtons per meter over a distance of 10 meters. What we're saying here is that if the weight of the beam is 5 kilonewtons for every meter of beam, then the total weight is 5 kilonewtons per meter times 10 meters, or 50 kilonewtons. Since the UDL is evenly distributed, then the average location will be at its center of mass. For a uniform beam, its center of mass will also be its geometric center, or at 5 meters from each end. So we can now replace the UDL with the equivalent point load. Now that we have the equivalent point load version of the problem, we can solve for the reactions in the same way as we did in the last video. We start by writing out the static equilibrium conditions for linear forces and for moments. Here we are going to ignore the horizontal directions as there are no horizontal forces. So the vertical static equilibrium equation is RA minus F plus RB being equal to 0. Here we're taking the upward direction to be positive. For the moments equation, we first need to choose a pivot point, so let's choose the left end of the beam at RA. Now we can write the moment due to each force. RA acts right at the pivot point, so its lever distance is 0. The next force is F, which points downwards and has a lever distance of 5 meters, so its moment is written as negative F times 5. The last force is RB, which points upwards and is 10 meters from the pivot point, so its moment is RB times 10. The total moment about the pivot point equals 0 for static equilibrium. As RA does not produce any moments, then the moments equation reduces to negative F times 5 plus RB times 10 being equal to 0. This equation allows us to solve for RB because that's the only unknown, by transposing the equation to get RB being equal to F times 5 divided by 10. With F being equal to 50 kilonewtons, RB is then equal to 25 kilonewtons. Note that the answer is positive, indicating that RB points upwards as expected. Now that we know what RB is, we can then solve for RA using the vertical force equations. So transposing this equation gives RA being equal to F minus RB, which is 50 kilonewtons minus 25 kilonewtons being equal to 25 kilonewtons. So in this example, RA and RB have the same magnitude of 25 kilonewtons. In other words, they produce the same reactions. This is expected since the load is at the center of the beam, and one would expect that each support will produce half of the reactions needed to counter the load. In our next example, we'll consider a beam with two distributed loads on it. The first load has a UDL of 5 kilonewtons per meter, distributed over the entire length of the beam, and the second load has a UDL of 2 kilonewtons per meter, distributed over the right 5 meters of the beam as shown in the free body diagram. Again, our supports will be located at the ends of the beams and the reactions given as RA and RB. For UDL1, its length is 10 meters, so the total force from that load is 5 kilonewtons per meter multiplied by 10 meters to give us 50 kilonewtons. For UDL2, its length is only 5 meters, so the total force from UDL2 is 2 kilonewtons per meter multiplied by 5 meters to give us 10 kilonewtons. Now that we know what the total load is for each UDL, we need to determine the points where they act. We already know from the last example that the equivalent point load of UDL1 is at the center of the beam because this is also where the center of mass is. We can now replace UDL1 with a point load F1 at 5 meters from the start of the beam. The location of the point load for load 2 is also at its center of mass, which will be the middle of its distribution. Since UDL2 is 5 meters long, then its center of mass is 2.5 meters from where it starts, which is at 5 meters from the left of the beam. So the equivalent point load location is 7.5 meters from the start of the beam. Now that we've converted all of the distributed loads into point loads, we can proceed to solve for the reactions. So let's write out the vertical force equation first. Writing in order of the forces from left to right, we have RA minus F1 minus F2 plus RB equals 0. Now for the moments equation, let's take our pivot point at RA and writing out the moments for each force relative to the pivot point gives RA at 0 meters, F1 pointing downwards at 5 meters from the pivot, F2 pointing downwards at 7.5 meters from the pivot, and RB pointing upwards at 10 meters from the pivot. With RA cancelling out to 0, we can transpose for RB to give RB being equal to F1 times 5 plus F2 times 7.5 divided by 10. And since F1 is 50 kilonewtons and F2 is 10 kilonewtons, this gives us a value of 32.5 kilonewtons for RB. Now that we know RB, we can substitute that into the vertical force equation and solve for RA. This gives us RA being equal to F1 plus F2 minus RB, or 27.5 kilonewtons. In summary, to solve for reactions on a simply supported beam where there are distributed loads, first convert those distributed loads into point loads by multiplying their UDL over the distance that they act along the beam. This equivalent point load will be at the load's center. For linearly distributed loads, this will be half of the length of the UDL. Once the equivalent load is determined and its location also determined, reactions can then be calculated using moments analysis.